Good morning, everyone. Okay, just a second. Oh. Okay, welcome to the linear algebra class, and we are considering the vector space. So before we consider these new topics, let me briefly consider some topics, concepts we considered in section 1 and 2. So we first extend the concept of the vector space. So previously, we considered an Rn space, right? And then when I say a vector in Rn, it was a matrix with a single column. Now we extended that concept to define something called a vector space, which is a set. And so when I say a vector space, it is a set which is closed on the addition of arbitrary elements and scalar multiplication, which means when you add any two arbitrary elements within the set, the result of the summation is also included in the set. And when you have one element and one arbitrary real number, when you multiply those two, you get another vector, another element in the vector space. And additionally, this addition and scalar multiplication satisfy the 10 axioms, right? For example, the addition is commutative and associative, and they satisfy certain distributive laws, and there exists a certain zero vector, and right? And also given any u, we can find another element denoted by negative u, so that their summation produces the zero vector, and so on, right? So there are 10 axioms, 10 properties which are satisfied when a vector space is given. So for vector space, it is closed on the addition of any arbitrary elements and scalar multiplication. Satisfying, and it satisfies 10 axioms. Right? So that is a vector space, and we considered several examples. We first considered the set of arrows, right? So we considered some arrows, and for that set, we define the summation and scalar multiplication somehow, so that the set of arrows satisfies all those 10 axioms, right? And as I said, that was a common example in engineering or physics department. And then we considered the set of sequences, right? And then we considered the set of some polynomials of degree n or less. And then in case of the polynomials, we studied how to add those two, right, during these middle school days or high school days. And we also considered some scalar multiplication between some polynomial and some real number, right? So under those definitions of addition and scalar multiplication, the set of polynomials of degree n or less, the set is a vector space, right? And then we considered something called a subspace. So when I say, so given some vector space, say V, one of its subset. So a subset H is called a subspace. Of course, the subspace of V if it is closed on the addition and scalar multiplication. In other words, if this set H is a vector space, then we say this subset is a subspace, right? And then we consider some examples. So given some m by n matrix A. In other words, given A, if I have an m by n matrix A, then that means given a linear transformation T from Rn to Rm, which maps such that the x is mapped to A times x. Given this mapping, okay, we could find some subspaces, right? The column space was the another name. It's defined by the collection of all the images of A times x. So that is the collection of the images when you consider all the vectors in the domain. So in the previous chapter, that was called the span of the columns of A, or when we define the transformation, that set was called the range of the mapping. So that was one subspace. This is a subspace of Rm space. And then the null space was the collection of vectors in the domain such that the image of those vectors is just 0. And that is a subspace of the domain Rn space. So those are some examples of the vector space, subspaces, right? Questions regarding those definitions? So there was one example at the end of section 1 in chapter 4 saying, if you consider given some vectors, say x1 up to xp in certain vector space, if you generate the space, okay, using those vectors, so x1, if you consider this set, this is space, this is set, the set of all the linear combinations of the x1 up to xp, then this set will be a vector space. And that is a subspace of V. So whatever these vectors, okay, x1 up to xp are, okay, if you consider the collection of all the linear combinations of the given vectors, then this set will generate a subspace or vector space. And so the column space, for example, is the collection of the images, and that is the collection of the vectors of this form, A times X. So column space is the space generated by the columns of a matrix, right? So that the column space is a subspace satisfying that example, the statement in the example. The null space consists of all the solutions to this homogeneous problem. And as we observed in some examples, when you solve that homogeneous equation, the solution X can be always written as a linear combination of certain vectors, right? And if you have, say, 3 free variables, then X can be written as a linear combination of 3 linearly independent vectors, right? So this null space was also considered as a space generated by certain vectors, right? Anyway, those are some concepts we considered on Wednesday, right? So a few days ago. So I just reviewed these definitions before we consider a new topic. And let me ask one simple question to check whether you really understood those concepts. So one simple example of a vector space is an R2 space. So this is a vector space. Oh, and one comment. As I said, R2 is not a subspace of R3 space, right? So that's what I mentioned several times. So please be careful. Please do not claim that R2 is a subspace of R3 space, okay? R2 consists of vectors with only 2 elements. R3 is a space with vectors with 3 elements. Okay, so there is no relation between these two. Now, given this R2, which is a vector space, if I consider, say, H, which consists of 2 vectors with 2 components in R2, such that, for example, X times Y is non-negative. If I consider this a set, is H a subspace of R2? Is H a subspace? Yes, I mean, if it is closed under the addition and scalar multiplication. In other words, when you add any 2 arbitrary elements in H, and when you add them, you get a vector, some element in H. And when you multiply any number to an element in H, and if you get an element in H, then this H will be a subspace. Or, in other words, is H a vector space? Yes? So I'm just considering the elements in the first quadrant and the third quadrant, right? So that defines H. Now, if I consider some elements like, say, 1 and 4, that is in H, and say -3 and -2 in H. If I add those two, 1 and 4 plus -3 and -2, you get -2 and 2. Okay, that is somewhere here, which is not in H. So this set H is not closed on the addition. So this H is not a subspace of R2 space. Because it is not a vector space, right? So please be careful, okay? You need to consider some extreme situations, okay? And if you have any counterexample for these 10 axioms, then the given set is not a vector space or subspace of some vector space, okay? So please be careful. Oops. Okay, now this concept is quite similar to the definition we considered in the previous, in earlier section. So given some set of vectors, we say these vectors are linearly independent if the information carried by these vectors are not, the redundant. I mean, when you have the linear combination of the given vectors is 0. That happens only when all the weights are 0. In that case, the given set will be linearly independent. Otherwise, in other words, if you can generate the 0 vector using these vectors with some C1 up to Cp, not all 0, which means some of them may be 0 valued, but at least one of those P coefficients is not 0. In that case, we say the vectors are linearly dependent. If you have a linearly dependent vectors so that they produce this 0 vector with possibly at least one non-zero coefficient, then such relation will be called linear dependency relation. So we considered some examples previously. So if I have, say, vector of 1, 2, 3, 2, 1, 0, they are linearly independent vectors. But if I have any, say, 0 vector, then I can multiply some non-zero value to that 0 vector and zeros to those non-zero vectors. And then if you add them, you get the 0 vector. So these 3 vectors will be linearly dependent. That's what we considered in the previous section, right? Now, in this new extended concepts, when I consider, say, P2 space, so that is the collection of all the polynomials of degree 2 or less. So that's the collection of all the polynomials, say, A0 plus A1t plus A2t squared type polynomials. And as I said at this point, A0, A1, A2 can take any real number. So A1 or A2 can be 0 valued. So in that case, this P2 will be a vector space. And in that set, okay, so the constant function 1 and the function t and t squared will be linearly independent because A0 times 1 plus A1 times t plus A2 times t squared, that represents an arbitrary polynomial in P2 space. And if that equals identically 0, that equality means, so here this equality implies that the left-hand side will be always 0 for any value of t. Okay? So that happens only when A0, A1, and A2 are all zeros. That's what we learned in high school days, right? So the set of 1, t and t squared will be linearly independent. We can easily show that 1 plus t plus t squared will be also linearly independent, because a naught times 1 plus a1 times 1 plus t plus a2 times this polynomial equals 0. That implies that the left-hand side can be rearranged to generate a1, a naught plus a1 plus a2 times 1 plus a1 plus a2 times t plus a2 times t squared equals 0. And if that is 0, then this statement implies that the corresponding coefficients a naught plus a1 plus a2 equals 0, a1 plus a2 equals 0, and a2 equals 0. If that's the case, since the third row implies that a2 is 0, if I combine that fact with the second equation, because the value of a2 is already 0, the second equation implies that a1 is 0. If a1 and a2 are both the zeros, then the first equation shows that a naught is also 0. So if this is the case, or when you solve this system of three equations, then a naught, a1, a2 are all zeros. So the set of 1 plus t, and 1 plus t squared will be also linearly independent. Right? If you take the, so what else? Oh, if I consider the set of 2 by 2 matrices, this V is a vector space, right? If I consider the set of, say, A0, 0, D type matrices, this is a vector space. So in other words, H is a subspace of V, right? In H, 1, 0, 0, 1 and 1, 0, 0, negative 1 are linearly independent. This is linearly independent in H, right? Because if you consider, say, any linear combination of those two vectors, say A times 1, 0, 0, 1, plus, say, B times 1, 0, 0, negative 1, and then if you set this to be 0, which is the 0 matrix, then the left-hand side implies that A plus B, 0, 0, A minus B matrix, and then the equality between these two matrices imply that the corresponding entries are the same. So A plus B will be 0 and A minus B equals 0. If you solve that equations, then you can show that A and B are both 0. So if I assume that certain linear combination of the given vectors is 0, then the weights will be 0. So because of this, the given vectors will be linearly independent. Do you follow me up to this? And what if I consider, say, for the same subspace, if I consider, say, 1, 0, 0, 1 and 1, 0, 0, 2, and say 2, 0, 0, 2 matrix. If I consider the set of these three matrices, then as you can see, if I multiply -2 to the first matrix, and then 0 to the second matrix, and then 1 to the third matrix, this sum will generate the 0 matrix. So the given set will be linearly dependent, right? So we just consider it, okay, some definition which is now extended to general vector space. So previously we considered vectors in Rn space, right? And then given those vectors in Rn, we could tell whether the set is linearly dependent or independent. Now, I want to extend that concept to general vectors in some general vector space. Then we have this theorem, okay? An index set of P vectors from V1 up to Vp, okay? From some vector space, okay? Some vectors, okay? So V1 up to Vp may be those vectors in Rn, or this V1 up to Vp can be polynomials, or some matrices, or some sequences, okay? So given any arbitrary vector space, if I consider the set of P vectors in that space, that will be linearly dependent if and only if one of the vectors is a linear combination of the preceding vectors, or it is a linear combination of the other vectors. So V1 up to V sub j minus 1 and say V sub j plus 1 up to Vp. So if some vector can be written as a linear combination of the other vectors in that collection, then that collection will be linearly dependent. Okay? And this theorem 4 will be a quite useful fact. So when a set of vectors is given, and if you want to check the linear independency or dependency, you need to check whether some vector can be written as a linear combination of the others. And the proof is the same as that of theorem 7 in section 1.7. So we are not going to consider that proof. Okay. Now, given some set, okay, based on this theorem 4, I can tell whether the set is linearly dependent or independent, right? Or we can use the definition, right, to check whether a certain set is linearly dependent or independent, right? Now, suppose that I have a vector space of V, okay, and H it's a subspace. Then we say some set of vectors B, okay, is a basis for H space if this B is, first of all, linearly independent, and H equals span of B. Okay? I said H equals span of B. So equality between H and span of B means H is contained in span of B, and also span of B is contained in H, right? So when I say H equals span of B, then that means H is contained in span of B, and span of B is contained in H. in that case, okay, in that case, we say B is a basis, okay, for H space. Many students, okay, do not consider this second requirement as important, okay? But I say B is a basis for H if B is linearly independent and H and span of B are equal. Many students just considers only this one. Many students believe that if certain B satisfies that B is independent and H is contained in span of B, they believe B is a basis for H space. But span of B must be also contained in H as well, so that H and span of B must be the same. They must be equal. And B is linearly independent. That's the requirement for a basis. Okay? So H is contained in span of B, and also span of B is contained in H. Span of B is contained in H. Okay? So that's the requirement for a basis. So one example I'm considering is this. So suppose that I have two vectors, v1 and v2, okay, in some R3 space. Okay. Then their span will generate some subspace of R3 space. So if I call this set by H, then H is a subspace of R3 space. For any two vectors, v1 and v2, this H will be a subspace of R3 space. Okay? And when I consider this H, really many students believe that the set of E1, E2, E3, where these E1, E2, E3 are three columns of the identity matrix. Given these three vectors in R3 space, if I consider this set of E1, E2, E3, E1, E2, E3 is a basis for R3 space. Okay, but it is not a basis for H space for any vectors v1 and v2, because at least one of these three vectors will not be contained in the set H. Okay. I can prove that at least one of them is not contained in this set H. So this is not a basis for H space. But many students believe, I don't know why, but every year many students believe that this set of E1, E2, E3 is a basis for even H space, which is not correct. Okay. So sometimes not sometimes, but if I change the statement and suppose that H is a subspace of R3 space. And the set of E1, E2, E3 is a given. And let me call this set by S. And then if I make a claim that some subset of S is a basis for H space, if I claim this one, then that statement will be force in general, right? So this statement is force in general. This statement may be true in some situation, right? For example, if H equals R3 space, then that statement will be true, okay? Or if H is the span of E1, then some subset of this S will be a basis for that space. So that statement may be true in some situations. But in general, if I consider an arbitrary subspace of R3 space, then that statement may not be true, right? So mathematically, if I consider that situation, then that statement will be in general false, right? A basis is a linearly independent set of, so basis of V means some linearly independent set that spans V space. So as I said several times, so span of this basis must be equal to V. Okay, must be equal. In other words, the span of this basis must be contained in V space, right? And the span of the vectors includes span of these vectors contain each vector. When I say some set of B1 up to BP is a basis of certain set H, then this B1 up to BP must be some vectors in H space. If any of the vectors is not contained in H, okay, then this collection of those vectors cannot be a basis, right? So please be careful when you choose a basis. If you want to define a basis, you must choose some vectors from the given set, given vector space. So, and suppose that I consider the columns of the identity matrix. So given Rn space, if I consider these n vectors of the n by n identity matrix, then any vector in Rn can be written as a linear combination of those vectors. Right? Given any vector, say x1 up to xn with these n numbers, that can be written as x1 times e1 plus x2 times e2 plus up to xn times en. So any vector in Rn can be written as a linear combination of these n vectors, and those n vectors are linearly independent. So these n vectors will define a basis in Rn space, and that basis is now called the standard basis for Rn space. So it is, okay, when I say the standard basis for Rn space, I imply those n vectors. But that's not the only basis for Rn space. So for example, in say R3 space, the set of E1, E2, E3 is the standard basis. And you can also show that E1, E1, oops, E1, E1 plus E2, E1 plus E2 plus E3 will be another basis. You can show that. You should be able to show this. Please check this, okay? So this is another basis. How about E1 minus E2, E2 minus E3, and E3 minus E1? Is this a basis? First of all, is this linearly independent? Yes? No? Why not? What kind of linear dependence relation can I derive?
1, 1, 1.
I'm sorry?
C1 is 1, C2 is 1, and C3 is 1.
Okay, so when I add E1 minus E2, E2 minus E3, and E3 minus E1, and then if you add them, you get the zero vector, so they are linear, it is linearly dependent, so it cannot be a basis, right? Then how about E1 plus E2, E2 plus E3, E3 plus E1? Are they linearly independent? Dependent? Is it a basis? Yes? No? So in order to check the linear dependence or linear independence, okay, what is the definition of linear independency? You consider a linear combination and then you set this combination to be zero, right? So C1 times E1 plus E2 plus C2 times E2 plus E3 plus C3 times E3 plus E1, you set this to zero. And then if you can confirm that E1, E2, E3 are all zeros, then the given set will be linearly independent. Right? So you need to check whether you can derive this effect from the given condition. Now, if I assume that the linear combination of three vectors is zero, and then if I rearrange these terms, then the left-hand side will be C1 plus C3 times E1 plus C1 plus C2 times E2 plus C2 plus C3 times E3, and that equals 0. If that's the case, then moments ago, I said E1, E2, E3 is the standard basis, saying E1, E2, E3 are linearly independent. If they are linearly independent, and if you generate the zero vector from this linear combination of those three vectors, then the corresponding coefficients must be all zeros, right? So if that's the case, then C1 plus C3 equals 0, and C1 plus C2 is 0, and C2 plus C3 equals 0. Okay? If you solve this system, you can solve this one, right? You can construct an augmented matrix with those numbers, and then you can perform the row operation to find the solution of this. If you solve the system, you get these three solutions only. There's no other solution for this problem, right? So E1 plus E2, E2 plus E3, E3 plus E1, this set of those three vectors is linearly independent. So the first condition is satisfied, right? So you still have one more condition to check, right? If you need to check whether this set spans R3 space. In other words, you need to check whether any arbitrary vector can be written as a linear combination of those three vectors. If you can also confirm that fact, then this set will be linearly independent. This set will be a basis, right? So this part only shows that the set is linearly independent. Okay, that does not show that this set spans R3 space, right? So at this point, I need to confirm the other property, okay? Questions? Okay, you don't have any question, right? Okay, so let us consider this theorem. So suppose that I have some set S, okay? That is a set in V space, and H is the span of S. Then if one of the vectors in S, for example, V sub k, is a linear combination of the remaining vectors in S, then the set S, okay, the set formed from S by removing V sub k still spans H. So that means span of S and span of the set without V sub k. So V sub k minus 1, and then I skip V sub k and consider V sub k plus 1 up to V sub p. The claim is that these two will be the same. Given two sets, span of S and span of these p minus 1 vectors, they are, okay, when I consider these two sets, first of all, the set on the right is definitely a subset of span of S, right? So, because if you generate any vector with those p minus 1 vectors, it is a vector in the span of S. Do you understand this? So if I choose any vector from the right-hand side, that will be C1, V1, C2, V2, up to CK minus 1, VK minus 1, plus CK plus 1, VK plus 1, up to CP, VP. So that is an arbitrary vector from the right-hand side, right? That can be written as that vector plus 0 times V sub k, right? So that is also included on the right-hand side. Now on the left-hand side. So that means the set on the right is a subset of span of S, right? Now, if I choose an arbitrary element from span of S, that will be C1, V1 up to CK minus 1, V sub k minus 1 plus CK, VK, and CK plus 1, VK plus 1 up to CP, VP. So that is an arbitrary element from the left-hand side. Now, what is the assumption here? We have the assumption that if that V sub k can be a linear combination of the other vectors, then that means this V sub k So we have C1 V1 up to Ck minus 1 V sub k minus 1. And this V sub k can be written as a linear combination of the other vectors. So say d1 v1 up to dk minus 1 vk minus vk minus 1 and dk plus 1 vk plus 1 up to dp vp. And if I have the other expression, then as you can see, you can rearrange these terms as C1 plus CK D1 times V1 and CK minus 1 plus CK DK minus 1 VK minus 1 CK plus 1 plus CK DK plus 1 VK plus 1 up to CK P plus CK DP VP. I mean, if you have a linear combination of those P vectors, I can express it as a linear combination of these P minus 1 vectors. If that V sub k can be written as a linear combination of the remaining vectors. So this one shows the inclusion of span of S in the left, on the right hand side. So these two inclusions show that these two sets are equal. Right? So if I have a set of P vectors, and if some vector can be written as a linear combination of the other vectors, then I can safely remove that vector of redundancy. Okay? Then the span of the remaining vectors will be still the same. Okay? Now, if that's the case, given some set of vectors, and H was the span of those P vectors, if there is any redundancy, based on the statement A, I can remove that vector. Then span of the remaining vectors will be still the same. In other words, the remaining vectors will still generate H space. Now I can repeat that procedure until when I have only linearly independent vectors. Okay? Right? At some point, the remaining vectors will be linearly independent. Then that means the remaining vectors is linearly independent and they generate the space H. Then by definition, that set, the remaining set, will define a basis. So at some point, after the elimination of some vectors, the remaining set will be a basis for H space. Then, as one example, given some m by n matrix A, we know that, suppose that A has the columns of A1, A2, AN. Then the column space was the span of A1, A2, up to AN. So these n columns will generate the column space. Right? right? That is clear. And I mentioned a few times that given a matrix, we can distinguish the pivot columns and non-pivot columns. Pivot columns, I claimed that they are linearly independent. And I additionally claimed that if you have any non-pivot column, that can be written as a linear combination of the pivot columns, or in particular preceding pivot columns. So if a non-pivot column can be written as a linear combination of the pivot columns, that theorem 7, tells you that. So I can remove those non-pivot columns when I generate this space, column space, right? So this will be generated by span of the pivot columns because, as I said, any non-pivot column can be written as a linear combination of the pivot columns. So I can remove those non-pivot columns when I generate this column space. And I mentioned that these column space are linearly independent. So this statement shows that this set of pivot columns of A will define a basis for the column space of a matrix. So if you can tell which columns in A are the pivot columns, then they will define a basis for the column space. Right? Questions? I already proved this statement, so let me skip this one. Okay. And consider this example. Let me mention one thing, okay? So given a vector space V, we can consider any subspace, and previously we considered the set of only the zero vector. That was called a subspace, right? This set of the zero vector is a subspace of H. A subspace of V, right? So if I call this by H, then H will be a subspace, right? Then for this H, there will be a certain basis, right? And we need to find a set which is linearly independent, and the span will be this H, okay? For this H, okay, the set of zero, not of vector space, okay? The set of zero is defined. Sorry, not the set of zero. Sorry about that. An empty set is defined, okay, as a basis for this zero space. The empty set. Note that some students want to consider the set of zero, okay, as a basis. Now, when I consider this set of zero, its span will be H. That is correct. The problem is that if I have the set of zero vector, that is not linearly independent. right? If I have a set of one vector, I said the set will be independent only when the set consists of a non-zero vector. If the set consists of 0, it is linearly dependent. Actually, if you consider any set with some zero vector in it, the set will be linearly dependent. So the set of zero vector is not linearly independent, so that even though it generates H space, the set of 0 is not a basis for H space. Okay? The set of 0, this zero space is a subspace of any arbitrary vector space. And in case of a basis, an empty set is defined as a basis for H space, not zero set. Please be careful. Before let us consider the example, which is trivial. Suppose that I have these three vectors in R3 space, and H is the span of those three vectors, then H is a subspace of R3 space, definitely. And in this example, V3 is a linear combination of V1 and V2. So based on the statement of the previous theorem, span of these three vectors, which is H, will be the same as the span of just two vectors, V1 and V2. Now, in case of V1 and V2, they are linearly independent because V1 is not a multiple of V2 and V2 is not a multiple of V1. So the set of V1 and V2 will be a basis for H space. Am I right? Of course, the set of V1 and V2 is not a unique basis. There may be some other linearly independent vectors which generate H space. Okay? I'm just saying that this set of V1 and V2 will be one example of a basis for this H space. Okay, so it is trivial, so let me skip this one. Now, in case of example 2, I have a matrix B, and in this matrix B is written already on reduced echelon form. Right? So this B is already in reduced row echelon form so that I can easily tell which columns are pivot columns in B matrix. Okay? Then each non-pivot column is, in this case, is a linear combination of the preceding pivot columns, right? For example, the B2 is 4 times the B1, and B4 can be written as 2 times the B1 plus negative 1 times the B3. So the column space, that is the collection of all the linear combination of those 5 columns, that can be generated with respect to only B1, B3, and B5. And B2 and B4 are redundant, right? The contribution from B2 can be regenerated using B1. So the span of B1, B3, B5 will be the same as the column space of B. So the column space of B will be the same as the span of B1, B3, B5. B1, B3, B5 is also linearly independent. So this set of B1, B3, B5 will be one basis for the column space of B. But there may be some other bases. Okay? So I'm not saying this is the only basis you have. There are many other different bases. But in case of a matrix, I can easily tell which columns are pivot columns. right? So it is very simple to choose one basis if I know the reduced row echelon form of a matrix. So the set of those three columns will define a basis for the column space of a B matrix. Okay? So if you have a matrix B in reduced row echelon form, I can easily find a basis for the column space. The question is, if I have a matrix A, okay, and when I perform a sequence of row operations to get this B matrix, then, and usually I am interested in the column space of A matrix, not column space of B matrix. So then, how can I find a basis for the column space of A matrix? Okay. So that is the question, and that's what we want to consider here. Okay. And the claim here is that the pivot columns of a matrix A form a basis for column space of A. Okay. So let us check the proof line by line first, and then let me consider some examples to simplify this proof. So given matrix A, okay, so here A is some m by m matrix. Okay, given m by m matrix, I want to construct its column space. Okay, that is simple, right? I can just generate the linear combinations using the columns of A matrix, right? Oh. So suppose that B is the reduced row echelon form of A matrix. Okay, then the set of pivot columns of B is linearly independent, right? So if I have a matrix in reduced row echelon form, then I can easily identify the pivot columns, and the set of those pivot columns will be definitely independent. That should be trivial at this point, right? And since A is row equivalent to B, the pivot columns of A are linearly independent as well. Does it make sense? Or in other words, do you feel comfortable with this statement? Since A is row equivalent to B, the pivot columns of A are linearly independent as well. So that means if the B in the previous example was the reduced row echelon form of a certain A matrix, then first, third, and fifth columns of A will be linearly independent. That is the claim. Okay, please think about it during the break. Okay, so let us have some 10-minute break, and then let me continue from that point with some example. Okay, and in the meantime, please check the attendance as well. Okay, so let's take a break for 10 minutes. Okay, then let me continue the second part of this proof. So here, A is row equivalent to B. Okay, the pivot columns of A are linearly independent as well. So what is the meaning of this? So we consider. So here, given A, suppose that when I consider a reduced row echelon sequence of row operations, then you get the reduced row echelon form, say B matrix. Okay, and suppose that this B is given as in the previous example. So we have B1, B2, B3, B4, B5, and suppose that for simplicity, this is B1, B3, B5 are the pivot columns. Okay? And B2 and B4 can be written as a linear combination of B1, B3, B5. So in the previous example, the B2 was, say, 2 times of B1, and B4 was 3 times B1 plus negative 1 times B3, and so on. So suppose that we have such simple situation. Okay, then B1, B3, B5 are linearly independent. The claim here is that if that's the case, then A1, A3, A5 are also linearly independent. So to prove that, so to show that, so the here claim is that A1, A3, A5 are linearly independent. So let me assume that the linear combination of those 3 columns are 0. So suppose that C1, A1 plus C3, A3 plus C5, A5 is 0. If I can show that this C1, C3, C5 are all zeros somehow, then that will prove that A1, A3, A5 are linearly independent. Okay, that's what I want to show, right? So in order to prove that these 3 columns of A are linearly independent, then I first assume that the linear combination of those 3 vectors is 0, and I want to derive this effect. Then A1, A3, A5 will be independent. If I fail to derive this, then the columns may be dependent. So given this set, and given this linear combination of 3 vectors is 0, then that means C1, A1 plus 0, A2 plus 0, C3, A3 plus 0, A4 plus C5, A5 equals 0, because when I add 0 times A2 and 0 times A4, the equation is still the same, right? If I have that vector equation to be 0, then that means I can rewrite this as a matrix equation. Matrix A times C1, 0, C3, 0, C5 equals to 0 will be the corresponding matrix equation, right? Now, how do I solve that equation? If I have that matrix equation, how do we solve that equation? We construct an augmented matrix, perform row operations, right? That's the one and only one strategy to solve the problem, right? So you will construct the augmented matrix with the coefficient part A and the right-hand side of vector 0, and you construct this augmented matrix. Given this augmented matrix, you will perform sequence of row operations. Now, when you perform the sequence of elementary row operations on this matrix, the coefficient matrix will be changed to, so this coefficient matrix of A will be transformed to B matrix, because this B is the reduced row echelon form. So the A will become B matrix. And whatever you have on the right-hand side, that will be changed. But since the initial right-hand side of vector is just a 0 vector, whatever you perform, that 0 vector will still remain the 0 vector. So the matrix will become this one. And then you will find the solution, right? In other words, this augmented matrix is representing some equation, right? C1 B1 plus C2 B2, okay, and so on. So, in other words, this is equivalent to showing that you have, so when you consider this, so this matrix equation will be equivalent to B times C1, 0, C3, 0, C5 equals to 0 problem. Am I right? So if I consider this equation with A matrix, okay, and since B is the reducible echelon form of A, that equation can be replaced by this equation. In other words, C1 B1 plus 0 times the B2, okay, plus C3 B3 plus 0 times the B4, which can be erased, and then C5 B5 equals to 0. Now I know that B1, B3, B5 are the pivot columns. In other words, they are linearly independent. This linearly independent set will generate the 0 vector only with 0 coefficients. So that 0 vector can be constructed only when these 3 numbers are zeros. I started with this assumption. I initially assumed that certain linear combination of these 3 vectors is 0, and I could derive that C1, C3, C5 are all zeros. So that means the set of A1, A3, A5 is linearly independent. So if I consider some pivot columns in A matrix, they are linearly independent. Okay? So that's the case. Now, what if I consider some non-pivot column or some other vectors? So this theorem, the statements I just erased show that if you consider the pivot columns, the set of pivot columns in A matrix, then the set is also linearly independent. And in case of B matrix, so if I choose linearly independent vectors from B matrix, then corresponding columns in A will be independent, right? Now, if I consider some linear dependent vectors in B matrix, for example, the set of B1 and B2 will be linearly dependent because they satisfy their linear dependency relation. So in case of B1 and B2, 2B1 minus B2 will generate the 0 vector. That means 2B1 minus B2 plus 0 times B3 plus 0 times B4 plus 0 times B5 is 0. In other words, given this B matrix, when I multiply 2, -1, 0, 0, 0, you get the 0 vector. In other words, the set of these 5 entries is one of the solutions for the homogeneous problem. As you solved in the middle term, the solution set for the homogeneous problem is not changed when you replace any coefficient matrix with its reduced row echelon form. Right? So note that the solutions for AX equals 0 problem will be always the same as the solutions for BX equals 0 problem. If the set is different, then there is no reason to consider the row operation. We consider the reduced row operation because that reduced row operation does not alter the solution set of this homogeneous problem. Right? Given AX equals to B problem, right, we construct the augmented matrix and perform the elementary row operation to convert it to the echelon form, right? But when the right-hand side is 0, whenever you consider the reduced row operation, the right-hand side will be always 0, right? In other words, the solution set for the original matrix A and the solution set for this homogeneous problem for the reduced row echelon form or any echelon form, the solution set will be the same, right? That's why we study the row operations. So when I consider this, B times this vector is 0, then when I consider that vector to A, you must have the 0 vector. In other words, 2 times of A1 plus -1 times A2 plus 0 times A3 plus 0 times A4 plus 0 times A5 must be 0. In other words, 2A1 minus A2 must be 0 as well. So given some vectors in B, if you have some linear dependency relation, in other words, given collection is linearly dependent, then corresponding collection of the columns in A will be also linearly dependent. Okay, so given the columns of A and given the columns of B, if you consider linearly independent columns in B, corresponding columns in A will be independent. If you consider linearly dependent columns in B, then the corresponding columns in A will be also linearly dependent. Okay? So that will prove the theorem, previous theorem. So what is the proof? What is the claim of the proof theorem? The pivot columns in A, okay, form a basis for the column space of A. So you need to identify the pivot columns in A matrix. I didn't say the pivot columns of the echelon form. I say, okay, or the textbook says, the pivot columns in original A matrix. That will form a basis for the column space of A. That is the claim in the theorem, right? Then, before we go to the next section, if B is the reduced row echelon form of A, then the question, if B is an echelon form of A, including the reduced row echelon form, is columns of B equals the column space of B. Is column space of B equal to the column space of A? Are they equal? Sometimes they may be equal, right? Sometimes. But are they equal in general? For example, what if A equals, say, 1, 0, 0, 0, 1, 0, and say 1, 0, 0. Then what is B? What is the reduced row echelon form of A? Well, in that case, the B will be 1, 0, 0, 0, 1, 0, and 0, 0, 0, right? If I subtract the first row from the third one, you get an echelon form, which will be the reduced row echelon form as well. Then, is column space of A equal to the column space of B? Okay, in other words, when I consider the column space of A is defined by the collection of linear combinations of the columns in A matrix. So, for example, the column space of A contains, say, 0, 1, 0 vector. It also contains 1, 0, 1 vector. Right? So the column space of A has 1, 0, 1 or 0, 1, 0 vector. They are included in the column space of A. Right? But when I consider the column space of B is generated by a linear combination of the column space in B matrix. And in B matrix, every column has 0 in the third place. So if you play with the columns in B matrix, the third entry of the resulting vector will be always 0. But the first column in A has non-zero entry in the third place. So that means this 1, 0, 1 vector is included in the column space of A, but it is not included in the column space of B matrix. So column space of A and column space of B cannot be the same in this example. Right? So column space of A and column space of B are different. That's why in the theorem, when I consider a basis for the column space of A matrix, okay, you perform the row operation to derive the reduced row echelon form. Once you have the reduced row echelon form, you can identify the pivot columns of that reduced row echelon form, and also you can find the pivot columns of the original A matrix. Now, if you want to find a basis for the column space, you must go back to the A matrix and choose the pivot columns in A, not B, okay, to define a basis. Okay? So, in general, the column space of A and column space of B, if B is an echelon form of A matrix, then they are different in general. In some extreme situation, they may be the same, okay, but in general, they are different. Okay? But the pivot columns in B will form, this is the basis for the column space of B. And if you consider the pivot columns in A, then that will be a basis for the column space of A. Okay. So in order to find the basis for column space of A, you need to perform the row operations to derive an echelon form. So in the echelon form, the pivot columns are those columns having the pivot positions, right? So you identify those pivot columns in B matrix, and then you select the corresponding columns in A to define a basis for the column space of A matrix. Okay, so when you perform the row operations to derive an echelon form or reduced row echelon form, you can identify the pivot columns there, but before you choose the columns, you must go back to the A matrix and select those pivot columns in A to define a basis for the column space of A matrix. Okay? So please be careful. So the pivot columns of A are evident when A has been reduced only to its echelon form, right? When I have just A, it is very difficult to identify the pivot columns. To identify the pivot columns, you need to perform the row operations to derive an echelon form. Once I have an echelon form, you can identify the pivot columns, and you need to choose the corresponding columns in original A matrix to identify the pivot columns there, and they will form a basis. So please be careful to use the pivot columns of A matrix for the basis of the column space of A, not the pivot columns of the echelon form. And many students make a mistake with this part. So if I give you a matrix, and then if I ask you to find the basis of the column space, many students make a mistake with this one. They just choose the columns of the echelon form, and please do not make such a mistake. Now, if two matrices A and B are row equivalent, that means one matrix, say B, can be obtained from A by performing a sequence of row operations. In that case, the row spaces are the same. Row space of A and row space of B will be the same. So if, in particular, this B is in echelon form, then the non-zero rows of B form a basis for the row space of B. And since two row spaces are the same, those non-zero rows of B will form a basis for the row space of A as well. Okay. So, but that is trivial, right? I mean, first of all, if B is an echelon form of A, so that they are row equivalent, then all these row operations are reversible. If B can be obtained from A by performing certain row operations, right, then A can be obtained from B, right, by performing another sequence of row operations. I can undo all these row operations, right? Then you can go back from B to A, right? Since row operations are reversible, if one matrix is obtained from A by some row operations, then we can obtain this A from B, right, by performing similar row operations, right? Then, what is the row space? Row space is the space generated by some sequence of row operations. Span of the row operations. So, if A consists of, say, A1, A2, up to AM vectors, and if B is obtained from B1, B2, up to Bm, and suppose that this B is on echelon form of A matrix, then that means B1 is obtained from these M rows of A matrix by some row operation, right? Possibly with interchange or scaling or replacement, right? And in a similar way, B2 can be obtained from the rows of A by performing some row operations, right? In other words, if B1 is obtained from a sequence of row operations of the rows of A matrix, so if any row of B, say Bi, is obtained from rows of A matrix by some sequence of row operations, then, for example, in case of interchange operation, if A1 and A2 is interchanged to generate this B2, B1, then B1 can be written as a linear combination of A1 and A2. Right? If I consider a scaling operation, so if B1 is obtained from A1 by multiplying, say, 3, then that means B1 is 3 times A1. Right? If B1 is obtained by some replacement operation, then B1 can be written as a linear combination of 2 rows. Right? So if B1 up to Bm, if those are results of some row operations, then that means each Bi is a linear combination of rows of A matrix. And I said these row operations are reversible. If B is on echelon form A, then each row of B is obtained from the rows of A. In other words, each row of B is a linear combination of the rows of A. But I can undo these operations because row operations are all reversible. That means I can derive A matrix from the rows of a B matrix. In other words, each row of A can be written as a linear combination of rows of a B matrix. Right? Since row operations are reversible, I can consider this statement, okay, and claim that each row of A is a linear combination of rows of B matrix. So this upper part shows that if each row of B is a linear combination of rows of A, then that means when I consider the row space of B, okay, row space of B is generated by some rows in B matrix. And if each Bi is a linear combination of the rows of A, then that linear combination inside the row space of B is contained in the row space of A matrix. So this upper statement shows that the row space of B will be a subset of row space of A matrix. And this lower part shows that if each row of A can be represented by some linear combination of rows in B matrix, then that will imply that any vector in the row space of A is contained in the row space of B matrix. So if these two are satisfied, then the row space of A will be the same as row space of B. So that's one thing we can derive from this statement, right? So if B is obtained from A matrix by performing row operations, then row space of A will be the same as the row space of B matrix. Okay? Then, when I have an echelon form of certain matrix, by definition, if you have any row of zeros, it will be located at the bottom of the matrix. And above those zero vectors, you have non-zero rows, right? And by definition of an echelon form, each row has a pivot position. And those non-zero rows will be linearly independent. So let me erase this. So I just claimed that row space of A and row space of B will be the same when B is obtained from A by performing row operations. And if B is on echelon form, then the shape of that matrix will be, this B will be like this. You have some non-zero rows above with some pivot positions in those rows, and below those non-zero rows you have rows of zeros. That will be the shape of this echelon form. If I have those non-zero rows above here, these non-zero rows, of the echelon form are linearly independent. So row space of A will be the same as row space of B, and row space of B is generated by the linear combination of those rows in B matrix, and since the contribution from the zero vectors can be discarded when I construct the linear combination, the row space of B is obtained, right, from those non-zero rows, right? So the row space of B will be the same as, so if B is obtained from A, then as I wrote down at the bottom, the row space of A will be the row space of B. That's what I claimed moments ago. And that will be the same as, by definition, that is the span of rows in B matrix. But since these zero rows do not contribute anything, when I consider the row space, which is the span of the rows in B matrix, that will be the same as the span of non-zero rows in B matrix, right? I mean, if I have zero row, I can discard it, but still the span will be still the same. And as I said, these non-zero rows are linearly independent. So these non-zero rows will be a basis for so from this non-zero rows in B form a basis for the row space of B. And since row space of A and row space of B are the same, that will be a basis for row space of A as well. So I just found one basis for the column space and one basis for the row space, right? In order to find a basis for the column space or row space of any A matrix, I need to perform a row operations to get an echelon form B, right? And then I can identify the pivot columns in B. And then if you go back to A and choose those corresponding pivot columns in A matrix, then they will form a basis for the column space of A. And then this slide shows that if I consider non-zero rows in B matrix, then those non-zero rows in B will form a basis for the row space of B and also row space of A matrix. Suppose that B of 1 0 0 0 0 1 0 0 0 0 0 0 is a reduced row echelon form of A matrix. Okay? And suppose that A1, A2, A3, A4 is four. Okay, these four are four columns of A, and suppose that this uppercase A1, A2, A3 represent three rows in A matrix. Okay, then the previous theorem claims that when I choose the set of A1 and A2 in A matrix, that will be a basis for column space of A. Okay? And non-zero rows in B. So the vector of 1 0 0 0 and 0 1 0 0, the set of these two vectors is a basis for the row space of A matrix. Okay? So in the textbook, the author just follows the same style. And so the author uses the row vector of 1 0 0 and 0 1 0 0, right, to represent these two rows in B matrix. And if you want, you can rewrite this as 1 0 0 0 and 0 1 0 0, like this column style. Okay, so that is fine in our class. Okay, and any format is fine. Okay. My question. If I go back to A matrix and choose the first two rows in A matrix, is this a basis for the row space of A as well? Is it true in general? When I ask true first, okay, I'm asking, is that true in general? I'm not considering some extreme situation, but in general. So in case of the column space, I must go back to the A matrix and then choose the corresponding columns in A matrix. Okay? You cannot choose the columns in B matrix. So my question here is that in case of the row space, do I have to go back to A and choose first the two rows in A to define a basis for the row space? Or do I have to stay in B matrix? So let us consider some simple situation when A consists of 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0 case. In that case, B is the reduced row echelon form of A matrix, right? But the problem is that these first two rows in B are not linearly independent because they have the zero vector. So the first two rows in A do not form a basis in this case. So in case of the row space, you must stay in B matrix. You do not go back to A. Okay, you need to choose non-zero rows in an echelon form. Okay, they will form a basis for the row space. So this is the difference between the row space and the column space. Okay, even though the row space of A equals the column space of A transpose, so the row space is a certain column, is a column space of a certain matrix. But when you consider these bases, you need to be careful. And so the row space is a subspace of the domain of this mapping, right? Column space is a subspace in the codomain. For this column space, the range of the mapping, that is generated by the columns of A. And if you choose one basis, you need to identify the pivot columns in the original matrix. Okay? In case of the row space, you need to derive an echelon form, and then you need to choose non-zero rows of those echelon form to find a basis. So please be careful. So if B is in echelon form, the non-zero rows are linearly independent, and they will form a basis of the row space of B. Okay? And you must stay in B matrix and choose non-zero rows there, okay? And you do not want to go back to A matrix. So let us consider this matrix A. So this A is given as a 4x5 matrix. When I perform some row operations, I can derive an echelon form B. This echelon form B says A has B has 3 pivot columns, right? B has 3 pivot columns. So the corresponding columns in A will form a basis for the column space of A matrix. Okay? B1, B2, and B4. So B1, B2, and B4 will form a basis for the column space of a B matrix. So B1, B2, B4 is a basis for the column space of B. But that column space of B is different from column space of A. And if you want to find the basis of column space of A, you need to choose A1, A2, A4. So that will be a basis for column space of A. And the echelon form B tell you that first three rows are non-zero rows in B matrix. So those three non-zero rows in B will be a basis for the row space of B, but in case of the row space of B equals row space of A. So for this row space of A, these three rows in B will form a basis. But you do not want to go back to A matrix. Now, given B, okay, so given B, for the row space, these three non-zero rows in B will form one basis, because this B is one of the echelon forms, okay, of A matrix. And as I said, this B matrix tells you that first, second, and fourth columns in B are linearly independent. Then the corresponding columns in A will be also linearly independent. So for the column space of A, first the three columns in A matrix, the first, second, and fourth columns in A are a basis of the column space of A matrix. And if I go a little bit further, then I can derive the reduced row echelon form. So I have this as my reduced row echelon form of A matrix. Now, these three non-zero rows in C, okay, these non-zero rows in C will also define a basis for the row space. So this is a basis for the row space of C, and in case of the row space, that will be the same as row space of B, and that will be the same as row space of A. So these non-zero rows, three vectors, will define another basis of the row space of A matrix. Now, questions up to this? Now, given this C matrix, okay, if I want to find the null space, as I said, from A to B, B is considered because the null space of A, that is defined by the solution set of this homogeneous problem. And that solution set will not be the same, will not be changed when I replace this A with its echelon form or even reduced row echelon form. They are the same, meaning the null space of A will be the same as the null space of B or even null space of C. So when I consider the subspaces in this domain, row space of A, row space of B, row space of C are all the same. And null space of A, null space of B, null space C will be all the same. So to find the basis for the null space, okay, I need to first describe the solution set for each vector in this null space. I need to describe the arbitrary solution vector in terms, okay, and then I need to check what kind of vectors will generate the vector in the null space. So to identify this, I need to find the solution set for this A or B or C. So in other words, I need to consider this homogeneous problem. So the solution set for AX equals to 0 will be the solution set for CX equals to 0. For this CX equals to 0, we have a very simple situation. The solution set can be described in terms of the free variables, right? So here, x1, x2, and x4 are the basic variables. We can describe x1, x2, and x4 in terms of free variables, x2 and x5, x3 and x5. So, given these three equations for the Cx equals to 0, I can describe the basic variables x1, x2, and x4 in terms of two free variables. Then the solution set X was described with respect to these 5 unknowns, and x1 was negative x3 minus x5. x2 is 2x3 minus 3x5. x3 is x3. x4 is 5x5. And x5 is x5. So that is the solution set, the solution in general, right? And that vector can be written as the sum of two vectors, one having only x3 components, and the other having only x5 components. In the first vector, each entry is a multiple of x3, so that can be written as x3 times negative 1, 2, 1, 0, 0. The second vector can be written as x5 times negative 1, negative 3, 0, 5, and 1 vector. And as I said, when I describe the solution of the homogeneous problem with respect to these free variables, those two vectors appearing in this expression are always linearly independent, right? And that can be easily checked by looking at the entries corresponding to these free variables. Two free variables are third and fifth entries. So when I look at third and fifth entries of these two vectors, we can easily check that the first vector is not a multiple of the second vector and vice versa. In other words, these two vectors are linearly independent. So any solution X can be described as a linear combination of those two vectors, and these two vectors are independent. So these two vectors will form a basis for the null space of A, or null space of B, or null space of C. Okay? Questions? Yes?
Are the basis of
For basis of which space?
of the row space of A unique?
Row space of,
A
yes?
for some matrix A, are they unique?
No. Whenever you say a basis, it is not unique. If it were a unique, if that was unique, then probably they would call it the basis, not a basis, right? So a basis is not unique. For any space, you have infinitely many different bases, okay? Except the zero space. The zero space has only empty set. But for all the others, you can have infinitely many bases. Okay? For example, if V1 up to Vp is a basis, I can double the first vector without changing the others. You can multiply, say, 2 to the first vector and 3 times 3 to the second vector, and if you do not change all the others, these are all bases of certain space. Because if you multiply 2 or 3, the independency is not changed, and you can still generate the same space. So bases are not unique. But the non-zero rows of an echelon form, but in case of the echelon form, in the example, from A, I considered some echelon form B matrix, and then I derived the reduced row echelon form C. So non-zero rows in B is one example of a basis for the row space, and non-zero rows in C is another basis. And these two bases will be different. Okay, so before we go to the next slide, the number of pivots, the number of pivot columns, that has a very important, action. So please remember, note that in the examples, the number of vectors in the column space of A was the number of pivot columns and that was the same as the number of, the number of vectors in a basis for the column space of A is the same as the number of pivot columns, and that is the number of vectors in a basis for the row space of A. Okay, so, right? The number of non-zero rows in an echelon form will be just the number of pivot columns, right? Right? But as I said, the row space is a subspace of Rn, and the column space is a subset of Rm space. So there is no relation between the actual row space of A and the column space of A. Okay, there is no inclusion between these two. Okay, but one common property between these two is that when we consider the basis, the number of non-zero rows in an echelon form will be the same as the number of pivot columns. So the number of vectors in the basis for the column space will be the same as the number of vectors in the base of the row space. That's what we could find in the previous examples. Questions? Is that clear? Okay.